Good afternoon. My name is Nilesh Raut. I belong to RC 1100, that is Pillai College of Engineering, Panvel. My group ID is _004. My group leader is Dr. Surabhi and the other team member is Asmita Patil. We have chosen a topic, nanotechnology, upon which OER is to be created. Let us have a look on various tools which are used in the nanotechnology field. There are various microscopic tools like atomic force microscope, scanning electron microscope, and the tunneling electron microscope. Out of these, the one which we are going to study here is the scanning electron microscope. Before the discovery of these particular tools, the development in this particular field was at atomic level. But as soon as the invention of the tools happened, it became possible to reach up to electronic level and to study the topological and morphological properties of various types of specimens. So in this particular video, we are going to have a look at following points. What is SEM? The working principle of SEM, the major components and their functions, the electron beam and specimen interaction volume and escape volume, the magnification, resolution, depth of field and image contrast, and various other aspects. If you look at this particular slide, it gives the comparison of optical microscopy and the scanning electron microscopy. The first picture shows the small depth of field which is due to the optical microscopy, which has low resolution, whereas the other picture in which the scanning electron microscopy is used gives high resolution and the large depth of field. The scanning electron microscope is designed for direct study of the surfaces of solid objects. SEM is a microscope that uses electrons rather than light to form an image. There are many advantages to use the SEM instead of the optical microscope. The magnification, depth of field and resolution of optical microscope is 4x to 1000x, 15.5 micrometer to 0.19 micrometer and 0.2 micrometer resolution respectively. Whereas if you go for scanning electron microscope, its magnification is 10x to 3 lakh x, its depth of field is 4 mm to 0.4 micrometer and its resolution is 1 to 10 nanometer. The SEM has a large depth of field which allows a large amount of the sample to be scanned at one time and produces an image that is a good representation of the three-dimensional sample. The SEM also produces images of high resolution, which means that closely features can be examined at a high magnification. The combination of higher magnification, larger depth of field, greater resolution and compositional and crystallographic information makes the SEM one of the most heavily used instruments in research areas and industries, especially in semiconductor industry. Scanning electron microscope gives a totally different imaging concept. Instead of using the full field image, a point-to-point measurement strategy is used. High energy electron beam is used to excite the specimen and the signals are collected and analyzed so that an image can be constructed. The signals carry topological, chemical and crystallographic information respectively of the sample's surface. There are various applications of the SEM. In topography, the surface features of an object and its texture can be studied. In morphology, the shape and size of the particles making the object can be studied. In compositional aspect, the elements and compounds that the object is composed of and the relative amount of them can, can be analyzed. Whereas in the crystallographic information aspect, the arrangement of grains in that particular object can be easily studied with the help of scanning electron microscope. Here is the inside look of the column of the SEM, wherein you can find the electron gun, gun alignment control, pneumatic airlock valve, condenser lens, objective aperture, scanning coil, objective lens, motorized stage, and the sample chamber. Let us see how an electron beam is produced. An electron gun is used to produce a fine and controlled beam of electrons which are then focused at the specimen surface. The electron guns may either be thermionic gun or field emission gun. The thermionic emission gun uses a tungsten filament heated by a direct current to approximately 2700 Kelvin, or LAB6 rod heated to around 2000 Kelvin. A vacuum of 10 raised to minus 3 Pascal is needed to prevent oxidation of the filament. Electrons boil off from the tip of the filament and they are accelerated by an acceleration voltage of around 1 to 50 kilovolt. Whereas in case of field emission gun, the tip of the tungsten needle is made very sharp with a radius of less than 0.1 micrometer. The electric field at the tip is very strong, which is very much greater than 10 raised to 7 volt per centimeter. Due to the sharp point effect, the electrons are pulled out from the tip by the strong electric field. Ultra high vacuum is needed to avoid ion bombardment to the tip from the residual gases. Electron probe diameter is less than 1 nanometer is required. The need of vacuum is when SEM is used, the electron optical column and sample chamber must always be kept in a vacuum, because if the column is in gas-filled environment, electrons will be scattered by gas molecules, which would lead to reduction of the beam intensity and stability. The other gas molecules which could come from the sample or the microscope itself could form the compounds and condense on the sample. This would lower the contrast and obscure detail in the image. Let us have a look on major components of scanning electron microscope and their functions. The first one is magnetic lenses. The condenser lens, that is focusing lens, controls the spot size and convergence of the electron beam which impinges on the sample. The objective lens final probe forming determines the final spot size of the electron beam, that is the resolution of SEM. The condenser lens. For a thermionic gun, the diameter of the first crossover point is approximately 20 to 50 micrometer. If we want to focus the beam to a size less than 10 nanometer on the specimen surface, the magnification should be approximately 1 part of 5000, which is not easily attained with one lens only. Therefore, condenser lenses are added to demagnify the crossover points. The third component is objective lens. It controls the final focus of the electron beam by changing the magnetic field strength. The crossover image is finally demagnified to an approximately 10 nanometer beam spot, which carries a beam current of approximately 10 raised to minus 9 to 10 raised to minus 12 angstrom. Sorry, 10 raised to minus 9 to 10 raised to minus 12 ampere. By changing the current in the objective lens, the magnetic field strength changes, and therefore the focal length of the objective lens can be changed. As you can see in this particular picture, The first image is over-focused, the second image is properly focused, and the last one is under-focused. In the first one, the current is too strong. In the middle one, the current is optimized, whereas in the last one, the current is too weak. In a sequence of components after objective lens, there are scan coils and a raster pattern. Two sets of coils are used for scanning the electron beam across the specimen surface in a raster pattern similar to that of a TV screen. This effectively samples the specimen surface point by point over the scanned area. Here you can see the physical appearance of the electron detectors and a sample stage. Let us move to the next aspect, that is electron beam and specimen interaction. As you can see in this particular slide, the incident beam falls on the surface of the sample, and after getting reflected, it comes out as an X-rays or Auger electrons or primary backscattered electrons or cathodoluminescence or secondary electrons, and they are detected by the respective detectors which are aligned in the scanning electron microscope. The detected X-rays give the thickness compositional information. The Auger electrons give surface sensitive compositional information. The primary backscattered electrons will give you the atomic number and topographical information. The cathodoluminescence can give the electrical information of the specimen, whereas the secondary electrons are able to give topographical information again. The secondary electrons are produced by inelastic interactions of high energy electrons with valence electrons of the atoms in the specimen, causing the ejection of the electrons from the atoms. These ejected electrons with energy less than 50 electron volt are termed secondary electrons. Each incident electron can produce several secondary electrons. The production of secondary electrons is topographical related. Due to their low energy, only secondary electrons that are very near to the surface can exit the sample and can be examined. The backscattered electrons are produced by elastic interactions of beam electrons with nuclei of atoms in the specimen, and they have high energy and large escape depth. BSE images show the characteristics of atomic number contrast, that is, high average Z appear brighter than those of low average Z. Here Z means atomic number. If eta increases with the tilt. The interaction volume of electrons with the surface of specimen depends on the acceleration voltage, that is energy of electrons, and the atomic number of the specimen and electron beam size. Regarding escape volume of various signals, the incident electrons interact with specimen atoms along their path in the specimen and generate various signals. Owing to the difference in energy of these signals, their penetration depths are different. Therefore, different signal observable on the specimen surface comes from different parts of the interaction volume. The volume responsible for the respective signal is called the escape volume of that signal. The dimensions of escape zone of secondary electrons is 10 nanometer diameter and 10 nanometer depth. For backscattered electrons, it is 1 micrometer diameter and 1 micrometer depth, whereas for X-rays, the diameter and depth is about 5 micrometers. During image formation and magnification process,